if you remember, we were talking about the Hilbert transform yesterday, and we looked at the properties of the Hilbert transform, and we were on our way to using the Hilbert transform for representation of bandpass signals, and that's our topic for today. We will look at how the concept of the Hilbert transform helps us to have a convenient representation of bandpass signals, any general bandpass signal, in terms of appropriate what we call low pass signals and a sinusoidal signal, right. So we will see that, and that's a very convenient representation and has many applications as we go along. Okay. So let's review what we talked about yesterday. We had just defined the concept of an analytic signal x of pt for a given real signal x of t as a complex valued signal whose real part is the given signal x of t and whose imaginary part is the Hilbert transform of x of t. Right. So this is the analytic signal. Right. And one of the motivations that I gave you for defining the signal is, of course we have to appreciate that a little more as we go along, is that while x sub pt is also called the pre-envelope of the signal xt, the magnitude of x sub pt, the modulus of x sub pt, would be the envelope of xt. Now the concept of envelope I try to give you by taking a specific kind of signal, particularly for example when a low pass signal mt multiplies a carrier kind of signal cosine omega naught t, and we found that the modulus of mt defines the envelope of this signal mt cosine omega naught t, right. However, not all signals may be of this kind, that is a low pass signal multiplied by a band pass signal, right. Whereas if you look at this definition of the envelope as I have defined here, this is valid for all kinds of signals. So in that sense, this concept of envelope is a generalization of the physical concept that we discussed yesterday. That physical concept was something that you could visualize by looking at the waveform, right. If you trace the peaks of that those oscillations, right, the peaks define the envelope, the trace of these peaks define the envelope. You don't necessarily have to look at the envelope in that way. You can look upon it mathematically in this particular way, and you will see later that if you proceed like this, you will get the same answer even for those kinds of signals, right. But then that's something that we will look at later. Right now let's proceed further and look at the spectrum of xpt. Okay, we are looking at the spectrum of xpt. Now can we do that? Let's take the Fourier transform of this. This will be x of f plus j times x hat f. Well, what is x hat f? Now this value for f greater than 0, what will be the value of x hat f? J minus j times xf, right. So what will happen to this? It will become minus j square minus j, so this equal plus, so it will become twice of x of f for f positive. What happens for f negative? It will become 0. Very interesting result. So what do you find? So if you were to plot this spectrum So suppose you had a spectrum like that for x of t. The spectrum of xt, let's say, extends from some frequency minus sub w, minus w to plus w, right? Then the spectrum of xpt or xpf would be extend, suppose this is a, so this will be 2a going from 0 to w. So it becomes a one-sided spectrum. From a two-sided spectrum for the real signal, you get a one-sided spectrum. Do you now see some further analogy between what we are doing here and what we do when we go from a real sinusoid to a complex sinusoid? A real sinusoid has a component at both f naught as well as minus f naught. A complex sinusoid has a component only at f naught, right? So we have done the same kind of thing for any arbitrary signal. The real signal has both negative frequency components and positive frequency components. This spectrum would be amplitude even symmetric, amplitude spectrum would be even symmetric, and the phase spectrum would be odd symmetric. The complex signal that we have constructed, the analytic signal that we have constructed, only has positive frequency components, just like the complex exponential, right? It has only a positive frequency component. Of course, if you want, you can also construct a corresponding signal with only negative frequency components. What will you have to do for that? Suppose I wanted only negative frequency components. All you have to define is a new signal x, call it x sub nf, right, which is equal to x sub nt, which will be equal to xt minus jx hat t. So such a signal will have only negative frequency components, but it will be also a one-sided spectrum. So the spectrum of x and t will look something like that. Right? So you see a direct analogy between what we are doing here and what we are already used to when we try to represent a sinusoid with a complex exponential as a real part of a complex exponential, right? So again here also the signal of interest, which is a real signal, is a real part of either xpt or xnt, right? The same relationship holds, very similar relationship. So the development is absolutely parallel to what you already use very frequently in the context of sinusoids. Only thing is now you can use it in the context of an arbitrary signal, right? So as you can see, therefore the concept of analytic signal that we have now fixed up is an extension of the concept that you already know for sinusoid signals. You agree with this, and you feel as comfortable as you do when you use complex exponentials for representing sinusoids? Okay. If that is the case, we can move forward and come to the main thing of interest to us here, that is the complex envelope representation of bandpass signals. This particular representation or this particular theory is particularly useful when we want to represent bandpass signals. So let us start with a signal x of t such that its Fourier transform x of f corresponds to a bandpass spectrum. Okay. So let us say we start with a spectrum like that. Bandpass spectrum, you understand what it means when I say bandpass spectrum? That means most of the energy of the signal will be centered will be contained around some non-zero center frequency, not around DC but around some finite non-zero center frequency, right. So there is a band of frequencies around which the signal contains most of its energy. Now when I plot a spectrum like this, like a triangle or anything, it's just a arbitrary shape that I have drawn to indicate the extent of the spectrum. The actual shape is not important here in our discussion. Whether take a triangle here or some parabola or something else is not important. It is only, and again we are looking at we are plotting only the magnitude plot here. If there is a phase plot, it will be it could be correspondingly plotted. So the main purpose of drawing these figures when I draw the spectrum is only to show the extent of spectral support on the frequency axis, right. What is the frequency band over which significant energy exists in the signal, or energy exists in the signal, right. For example, for this signal, suppose this is f0 minus b to f0 plus b, where 2b is the bandwidth. So we will say roughly 2b is the bandwidth of the signal. This signal has a bandwidth of 2b and has a center frequency of f0. Again, it is not necessary that the spectrum be symmetric around f0. I have drawn it, I mean, just like that. There is no particular significance of this symmetry. They don't have to be symmetrical. What is required to be symmetrical is the spectrum should be even symmetric around 0. Right? That is the required property of a real signal, the spectrum of a real signal. But there is no symmetry requirement around the center frequency of that you may want to define. I could as well have defined the center frequency anywhere in this band. Instead of showing it here, I could have shown the center frequency anywhere in this band. It really doesn't matter. Only thing is, if I do it, if it is actually symmetric, then it is better to denote it in the center of that spectrum. Suppose it is not symmetric, the value of f0 is not particularly important as long as it lies within the band. Right? You could choose it arbitrarily, right? But it has to be somewhere in the band that you are talking about. Fine. So this is the plot of x of f, or magnitude of x of f. Right now, assume that the phase spectrum is 0, so we can assume that this is the plot of x of f itself. It can happen. You can have the phase spectrum which is 0, right? Right. So for this band pass signal, there was a question here. You wanted to ask something? It's taken care of. Okay. So for this band pass signal, suppose I find the analytic representation of this signal. Let's go from x of t to xpt. What will be the corresponding spectrum? What will be xpf? It will only contain positive frequency components with twice the height of the. Suppose this is a, this peak value is a here. The peak value now will be 2a. The center frequency will remain f0. It will go from f0 minus p to f0 plus p, right? And the peak value will be now 2a. Right? And I know that this xpt corresponding to this spectrum would be a complex valued signal whose real part is xt and whose imaginary part is x, the Hilbert transform of xt. Can I see this signal, this spectrum in a different way? Can I see this spectrum as a translated version of some spectrum around 0? I can see that. I mean, imagine a spectrum of this shape here, and your frequency translated it to f0. And how do you do frequency translation? By f0 only, by multiplying it with an exponential, right? So therefore it stands to reason that I could represent this xpt as a frequency translated version of some low pass signal whose spectrum is this, right?
Will that be symmetrical?
May not be symmetrical. That will depend on whether this is symmetrical. May not be symmetrical. Therefore that signal may not be real. it can be complex.
There is no signal of center frequency.
Right?
There is signal of center frequency. Center frequency. It can be the center also.
No. Suppose we have chosen a particular bandpass center frequency f0, and I am shifting it. I am considering this signal as a frequency translated version of a low pass signal. The way the frequency translation is by an amount of f0. Right? So same shape, instead of centering it around f0, I will center it around 0. Okay. Let me first, instead of writing the expression, what I am saying is you can think of this as a translated spectrum where the original spectrum is like this, and the translation is by an amount f0. In this particular case, because I have taken this to be symmetrical, this looks symmetrical here, but if this was not symmetrical, this symmetry would not exist here. So all I am saying is there is a frequency translation relationship between this signal that I am defining here and the signal xpf, which is the analytic representation of our original bandpass signal. Are you with me, everyone? Now, how do I represent this mathematically? You just told me that if I call this signal x tilde t, suppose not, of course this is the spectrum of the signal, so what I am plotting here is not x tilde t but x tilde f here. This is a plot of x tilde f, and the corresponding time domain signal I am calling x tilde t. This signal is a low pass signal because its spectrum centers around 0, and in general it would be a complex valued signal. In general, in particular it could be real valued if the symmetry here exists, right? In general it would be a complex valued signal, and these two signals would be related by a frequency translation operation. That means xpt would be x tilde t multiplied with e to the power j2 pi f naught t plus, because it's shifting to the right. So you can think of xpt, maybe I should use the next page. As a frequency translated version of a low pass signal, complex valued low pass signal x tilde t, so that xpt is equal to x tilde t e to the power j2 pi f naught t. Now that's a very interesting way of looking at it, right? You already done half the job. What you have got is that the analytic version of the bandpass signal which was of interest to us can be expressed as the product of a complex valued low pass signal and e to the power j2 pi f naught t, a complex exponential, right? Fine. Any questions on this? Also, it's clear that this envelope of this signal would be equal to what? Modulus of this signal is what? The modulus of this signal, right? Right. Now let's proceed a little further. My final purpose is to express x of t, the original bandpass signal, in similar terms, right? Because what I have got right now is a representation not for x of t but for the analytic version of x of t. Suppose I want to go from here to x of t. What should I do? I should take the real part of the signal, right? X of t is real part of xpt. Okay. Now since I said that x tilde t in general could be complex valued, so x tilde t in general would have some real part and some imaginary part, right? Let me call the real part as x sub rt and the imaginary part as x sub it. Is it okay? I hope I am not using too much, introducing too much notation and confusing you. We have agreed that x tilde t is some low pass signal. We have also agreed that in general this would be a complex valued signal. So all I am doing is giving some notation to its real part and some notation for its imaginary part, nothing more than that. And what I would like to, just like I have a representation of x pt in terms of x tilde t, what I would like to find out is there a corresponding representation of the original bandpass signal in terms of these components, right? It's very simple. All you have to do is now substitute for x pt as this into e to the power j 2 pi f naught t and take the real part of that. So what will you get? So we will get x of t. What will be the real part of this multiplied with e to the power j 2 pi f naught t? x r t cosine 2 pi f naught t minus x I t sine 2 pi f naught t. And that's the result we are looking for. These two results are what we are looking for. Very interesting and very important results. So what do you find here? That the original bandpass signal x of t can be given a representation in this form, in this most general form, where it could be considered as sum of two product terms, right? One product term is of the kind x r t cosine 2 pi f naught t, the other product term is x I t sine 2 pi f naught t, right? The bandpass nature of the signal comes out from the fact that there is a sinusoid present at frequency f naught, right? What is important is it is a product of a low pass term and a single frequency term or a band pass term, right? So the band pass signal can always be thought of as a product of a suitable low pass signal, of an appropriate low pass signal with a carrier signal, right? That's what it really boils down to. A very significant result. For every band pass signal there is a corresponding low pass signal. That is, in the sense that from that low pass signal I can generate the required band pass signal by a simple frequency translation operation.
So is there xt low pass signal?
Yes.
Then what is the band pass signal?
What is which is
Which
low?
one is the band pass signal and which one is the low pass?
You tell me. We started with what was our assumption about xt?
xt is the low pass.
xt was band pass. We have forgotten. Our whole discussion on this point started with xt having this spectrum, right? We started with an xt which had a band pass spectrum, right? So our xt is band pass. We represented xt in terms of xpt as real part of xpt, that is still band pass, right? We represented xpt in terms of x tilde t, which is low pass. X tilde t is low pass means x sub rt and x sub it are both low pass signals. Is that clear? The real and imaginary parts of x tilde t are therefore both low pass signals. Right. So xrt and xit are both low pass signals. So this is a low pass, this is a low pass signal, this is a low pass signal, this is a low pass signal. This is a complex value low pass signal. These are both real value low pass signals, right? So I can represent xt, the original band pass signal, an arbitrary band pass signal, in terms of two low pass signals multiplied with quadrature components of a carrier. We call this quadrature components of a carrier. We call this cosine 2 pi f naught t as the in phase carrier and sine 2 pi f naught t as the quadrature phase carrier, right? And xrt therefore is called the quadrature the in phase component of xt, and x sub it is called the quadrature phase component of xt, right? So sometimes in fact you will find in the books the notation I here, x sub I here and x sub q here. right? Here I use the notation real part and imaginary part of x tilde t, but in many books you will also find the notation x sub I t here and x sub q t here to indicate that this represents the so called in phase component of x t, and in phase component is a low pass signal, and this represents the quadrature phase component of x t. This, so I can basically, what it also means is that a band pass signal can be resolved into two low pass signals, one of which is the in phase component, the other is the quadrature component. Alright. Any questions? Okay, let me explain again. I am saying that any band pass signal x of t, we have found a representation for it. Let me slightly modify the notation myself here itself. Let me call the real part now by x sub I t, although it is little confusing, but if I want to talk about in phase and quadrature phase, this is more appropriate, into cosine omega naught t minus, so I will call this x sub q t, right, sine omega naught t. These two carriers are quadrature components of the carrier e to the power j 2 pi f naught t, right? They are the real and imaginary, right? So you can think just it's a terminology. We call this as an in phase carrier and this as a quadrature phase carrier. And these two are the in phase and quadrature phase components of x t. That's all. And these are definitions, just to remember. So again, let me summarize. A given signal, a given band pass signal x t can be expressed or can be resolved into its low pass components, one of which will be in phase with the carrier, the other will be in quadrature with the carrier, right? Rather, one of which the in phase component of it will have two components, one of which is called the in phase component, the other is called the quadrature phase component. I think that's more appropriate rather than saying it is in phase with the carrier. That is actually meaningless, that doesn't convey anything, right? Okay, so that's a representation of band pass signals.
So all these things are preserving the amplitude of my low pass signal. I am taking the analytical part of the signal. I am ensuring that my amplitude part of the low pass signal is preserved.
I don't know whether that means anything. We have preserved whatever needs to be preserved.
And that's
we have gone from here to here with twice the amplitude. This will remain twice the amplitude here, right?
What all we need is only the amplitude.
Sorry?
What all we need is only the amplitude of the signal.
Need to do what?
To preserve, because when I am having a signal.
Yes, in this context, right. Now, how do these representations help us? This representation helps us in visualizing a band pass signal in terms of a low pass signal. So that itself is a very satisfying result, and you will find that something that you will appreciate more and more as you deal more and more with band pass signals. You will find that this representation makes a lot of sense, and whenever you want to analyze the behavior of a communication system to band pass signals, right, you like to say, okay, I like to feed a band pass signal to this, and then you like to mathematically model that band pass signal, right? And what is the mathematical model which is appropriate to use? This model. That is, assume that the input signal has this form and then proceed with the analysis, right? So very useful mathematical representation, keeping in mind that in this representation we have two low pass signals and a carrier. It really helps to define things very precisely, right? equally useful is the other representation from which we derive this one. This representation, right? Now let's see. In fact, this is in fact more powerful representation than this in some sense. When we do analysis, it has the same power that the complex exponential has vis-a-vis the real sinusoidal signals. For example, what I like to say is that the information bearing part of xpt is in fact where? It's in x tilde t. This is just happens to be the center frequency, and this is an exponential corresponding to the center frequency. It has no particular information bearing aspect, right? For example, it's a carrier. I could as well change this to f1 or f2 or f3. Certainly xpt will change and xt will also change, but the information bearing part will be still the same, right? So this representation is in that sense extremely powerful, and therefore it makes sense to think that as far as my processing is concerned, or as far as my analysis is concerned, I could do most of the analysis without even worrying about this part, right? In fact, that is the case. You could exclusively deal with x tilde t and get back to the result of processing or result of analysis by just multiplying whatever you have got with e to the power j2 pi f naught t, right? That's the power of this. Let me illustrate this by taking a very specific example. Have you understood what I am trying to tell you? But I will try to make it more clear by considering a situation where, let us say, we are dealing with a bandpass system whose input is also a bandpass signal, right? So at the input we have a bandpass signal. I want to illustrate how the theory that we have developed, how the representation that we developed helps us, right, in dealing with bandpass signals in systems. So far we have looked at signals in systems purely in terms of it could be any signal or it could be any system. Now we are specifying that both the system as well as the signal are bandpass in nature, right? And in dealing with such systems, how is it easy to how can we make it easy to deal with such systems? That's our concern here. Okay, bandpass signal is input, and so let's say this bandpass system has an impulse response HFT, right? And we are feeding an input signal which is x of t, which is bandpass in nature. For example, this could be a bandpass filter. You are familiar with bandpass filters? That means it will pass a certain set of frequency components in the neighborhood of some center frequency f naught, right? And obviously it will make sense to have a signal which has frequency components in that neighborhood. If it does not have any frequency components in that neighborhood, the output of the filter would be identically equal to 0, right? So it makes sense that input signal is also of at least some components around that neighborhood, and let's say it is a bandpass signal in the same neighborhood, right? And you want to shape the spectrum of the input signal by passing it through this filter, right? And let's say the output is y of t. I know how to deal with systems, so you say what is you say what is a big deal? If I know ht, if I know xt, I can find yt by involving xt with ht. But what I am saying here is, I know that both ht and xt, they are essentially bandpass in nature, so they will have this quadrature representation that we just discussed, right, or the complex envelope representation that we just discussed. Incidentally, this representation, I probably forgot to mention that, excuse me. This representation is usually known by the name of complex envelope representation, right? So Now if I talk about a complex envelope representation, it is this, where x tilde t is called the complex envelope. Now we have seen that the actually envelopes are both the real envelopes are both both of them are same, right? And this is called the quadrature representation. So both these representations have names. This one is called the quadrature representation. This is called the complex envelope representation. So h of t itself has a complex envelope representation, isn't it? Because h of t is also bandpass in nature. So I could think of this as real part of h sub pt. And what is h sub pt? H tilde t e to the power j 2 pi f naught t, right? I am just repeating what I have already said for x of t. Similarly, x of t is the real part of x tilde t e to the power j 2 pi f naught t. Are you with me? What will you say? Yes, we are keeping f naught same in both of them, because we are assuming that both the input signal and the bandpass signal can be considered to have the same center frequency, right? Now I want to find y of t, which is x of t convolved with h of t. Let us go through this process and see where do we land, right? After doing that, I want to make a few other remarks. Please remind me if I forget that, and that's also a very interesting remark. But let's first see what is the result here. So let's proceed. Let's use these two representations to find y of t, which is a convolution of h t with x t, which you can write like this, right? If I want to make use of this representation of h t and x t in this integral, how should I do? I should substitute for h t as this quantity or this term plus its complex conjugate, half of that. The real part of any complex number is the sum of a number and its complex conjugate divided by 2, right? So I could represent h lambda here. Lambda of course is a dummy variable which is minus infinity to infinity. I could write h of t as half of h tilde t e to the power j 2 pi f naught t plus its complex conjugate, right? So CC here represents denotes complex conjugation. Similarly, x of t can be written as half of x tilde t e to the power j 2 pi f naught t plus its complex conjugate, right? Therefore, y of t is a fairly mechanical operation that I am carrying out. So what will you get? You will multiply this with x t minus lambda. This has two terms. This will also have two terms. So when you multiply this, you will get 4 terms, right? Let me write down these 4 terms. When you multiply this, the first term with the first term, you will get 1 by 4 h tilde lambda x tilde t minus lambda. What will happen to, maybe I should explicitly write the expression first. Excuse me. Let me explicitly write y of t completely first so that there is no confusion. So y of t is, I substitute for half h tilde t e to the power j 2 pi f naught t, sorry, lambda, this also is lambda plus its complex conjugate into half x tilde t minus lambda e to the power j 2 pi f naught t minus lambda plus complex conjugate of this into d lambda. Well, complex conjugate also will contain half, so that's okay. So now if I proceed term by term, this is lambda here, right? What will be the product of the first two terms? This will be 1 by 4 h tilde lambda x tilde t minus lambda, and what happens to the product of these two exponentials? E to the power j 2 pi f naught t, because the lambda term will cancel off, right? And you can expect that the same thing will happen if when I multiply the conjugate term with the conjugate term, except that it will be conjugate of this whole term, right? So I can say it will be the conjugate of this whole term when I multiply this complex conjugate with this complex conjugate. Similarly, when I multiply across now this with the complex conjugate, what will you get? You will get 1 by 4 h lambda, h tilde lambda into x complex conjugate t minus lambda, and now what happens to the exponential product? It does not cancel off. You will get two terms, e to the power j 4 pi f naught lambda, and also a term e to the power minus j 2 pi f naught t. So okay, plus you will get a similar term which will be the conjugate of this term. I will keep this there for a while, see if I made any mistake in writing this. Is it okay? Okay. Now what can we say about the third and the fourth term? Let's look at the third term. Can you say something about the third term? Let me claim that it is 0. Would you agree with this? Can anyone justify my claim here that the third term and therefore the fourth term would be both equal to 0? Integral is around this center. What does that mean? I don't understand that. No, we are just carrying out an integration with respect to the variable lambda, right? Of course, this term e to the power j 2 pi f naught t and e to the power minus j 2 pi f naught t, they come outside the integral, right? Because integration is with respect to lambda, so you don't even have to look at this term and this term. But look at the rest of the integral. You look at this part. Concentrate on this part. I claim that this integral is 0. Would you agree with this, and can you give me a reason for that? No? Okay, let me explain. What kind of a signal is this? What kind of a entity is this function? It's a low pass thing. What about x? X tilde? That's also low pass. What is this? This is a carrier. Let's say f naught is sufficiently high, right? What will happen now? What it means is that the rate of variation, time variation in these functions is small as compared to the rate of variation of this sinusoid. The rate of fluctuations here is much larger. So if I consider, let's say, one cycle of this sine wave, right, which that cycle is completed very fast, right, over that cycle this hardly changes, this function hardly changes, right? it remains more or less constant. Assuming that this is varying much more slowly than this will be so. In which case, what will be the value of the integral over one cycle? 0. And when I am integrating of infinity, half cycle by half cycle, the same argument can be repeated, right? And therefore, it boils down to saying that this integral is 0. So, basically the argument that we give here is based on the fact that this is a low pass signal and this is a high frequency band pass signal, right? And therefore, half cycle by half cycle, this kind of argument is very useful in communication theory, because otherwise you get stuck with integrals which you can't look at, right, which you can't evaluate. So half cycle by half cycle, integral becomes 0. Okay. The argument is simply this, that the integrand is a product of two functions. This part of the function is a low pass function and varies very slowly, fluctuates very slowly. We are assuming here slowly enough so that over one cycle of this remains more or less constant, and therefore the over one cycle the integral is 0. Repeat the argument for every cycle and therefore the integral becomes 0. Okay. So what happens to the result? This term is 0, this term is a conjugate of this term, so that will also be 0. So therefore basically we will be left with the first two terms, right? And what are the first two terms? If you look at this, think of this e to the power j2 pi f naught t separately from this integral, right? And the corresponding term there will be e to the power minus j2 pi f naught t. So you have some real, so you have something into e to the power j2 pi f naught t plus the conjugate of this into e to the power minus j2 pi f naught t, right? I can write that as, so y of t, I can write that as half of the real part of h tilde t convolved with x tilde t e to the power j2 pi f naught t, right? You agree with this? Let me put this both in front of you and hide the complicating fact. Okay, what I am saying is that these two terms is equivalent to writing this, right? This is nothing but a convolution of h tilde with x tilde, right, which is what I have written, okay, into e to the power j2 pi f naught t. And since you are adding a complex bit of that, what are you doing? You are taking the real part of that, twice the real part. So that's why your factor becomes 1 by 2. Fine. Look at it carefully. If you have any question, let me know. This is what I am writing here as like this. Okay.
The ideal part of e to the power j2 pi f naught t, that could be outside.
Yeah, it is outside. Could be outside. Doesn't matter.
So whatever the case may be, y will always be real.
Yes, it has to be real. But it is also turning out to be real because you are adding something, some complex quantity with its conjugate. So it has to be real and it is turning out to be real. So I have not found, I mean, there is no inconsistency here. X of t was real, h of t was real, therefore yt has to be real, it is turning out to be so. Right? And we are writing it as a real part of this. Fine?
But if xt and xt are
Not real. Even then you get yt to be real.
If what?
If xt and
No, we are starting with xt and ht being real, because normally we deal with real signals. This complex thing that we have introduced is a representation, right? Remember that I have got a complex envelope representation, but it's a representation of a real bandpass signal. Don't forget that the complex exponential is a representation of a real sinusoid. Similarly, the complex envelope representation is a representation of a real bandpass signal. Okay, in the same sense, we have used representation and see what result we get and whether it simplifies anything for us. We have not yet looked at the simplification aspect. We are coming to that now. Okay. Let me just complete. Okay, just one minute so that the argument is completed. So now let's look at this. This is the final result we got. Can I write like this? Half of real part of say y tilde t e to the power j2 pi f naught t, where I define y tilde t to be the convolution of h tilde t with x tilde t, right? And this is a result which has a lesson for us, the most important lesson which I want to talk about in this discussion. We could have avoided all these lengthy integrations that we have just gone through if we had recognized this fact, and this is what I was trying to say in the beginning. I don't have to carry out a convolution of a bandpass signal with the bandpass impulse response. I could as well do the convolution directly of the low pass representation of the bandpass signal, complex representation of the bandpass signal, with the complex representation of the complex low pass representation of the bandpass system, bandpass impulse response. Find out what the output would be, which will be obviously a low pass signal, a complex low pass signal. Then go and do this operation. So I totally can avoid working with bandpass signals, even though even though my basic interest is in working with bandpass signals, right? And the advantages that accrue are that I don't have to write those lengthy trigonometric expressions which will always be there in the bandpass signal representation, right? Because it is xrt cosine 2 pi f naught t, xit sine 2 pi f naught t, etc., etc., right? Or even the complex representation, I keep on carrying that e to the power j2 pi f naught t, e to the power j2 pi f naught lambda, t minus lambda. Those terms are not necessary to carry with us all in all our manipulations. Directly deal with the low pass representations, carry out your manipulations, carry out your mathematics, and the final result will be this, right? This is the point, because these carry the information. This is just carrier term to be added, right? So we will stop here and we will continue at this point. Thank you very much.